because accelerations are caused by an excessive amount of force that causes things to go faster and faster, or friction slows you down, kind of thing. So forces cause accelerations. The beauty of the next unit is it'll have less equations. So this is the big, heavy, lots of equations and relationships thing. I was just talking to Davenport. She said, yeah, people are still having questions about where does this go? What is this? Make sure if it's an acceleration, it goes in for A. If it's a distance traveled, it goes in for either delta X or delta Y. Velocities are speeds. V is velocity or speed. T is time as you do that. But real quick, we're going to do number 24 here. This has 3 different forces acting on an object. And the process of vector addition, this is a bonus problem, number 3, bonus 3. It says, first of all, you're going to break the vectors into parts. What does that mean? Well, that means that you're going to have something that has an amount and a direction, and we're going to take the amount, the quantity, times the cosine of the angle, or the amount times the sine of the angle. Always the cosine is going to give you the x part, and the sine is going to give you the y part. We're going to do that for every single vector. And then we're going to add x's with x's, y's with y's. Because we're going to make a giant triangle where if you have, here's all the x's. Oh, I'm going to use a notation here. It's Greek, and they do this in math. Sorry, it's a mathy thing. They will sometimes use a capital pi for the product, where you multiply things together. But we're not ever going to use that one. But they use a Greek sigma, a big, looks like an E thing, to mean the sum. It's an S for sum. Add them up. So we're going to sum the x parts. So the second thing we're going to do is we're going to add like parts. We're going to add x's with x's, y's with y's. This is where probably the trickiest part of it is, because it's secretarial, it's bookkeeping. You've got to be orderly and add x's with x's, y's with y's. Don't add x's and y's together unless you use the Pythagorean theorem, because one's going this way and the other's going that way. And so we sum the x parts to get a total. And so a lot of times they'll use an R for the resultant. It's like the total resultant x parts. And we're going to sum the y parts to get the total resultant in the y direction. And now you're going to have a giant triangle with the resultant of the x here and the resultant in the y here. And so to get the total amount, you're just going to do the Pythagorean theorem. X parts squared plus y parts squared square root. That will give us R, the total. And so the third part is Pythagorean theorem, which is why we're breaking it into parts and adding x's and y's so we can get a giant triangle. And then we can just do the Pythagorean theorem, and to get the angle, and this is the weird one, but the angle is going to be the inverse tangent of, always take the y over the x. And if you take opposite over adjacent, y over x, you will always get the angle to the x-axis, the horizontal angle. That's the direction. So those are the 4 steps. Like I say, it's bonus on this one. We will get to where we're doing this with forces, and in fact, this will be on the final. This is, I know how sometimes it seems like, oh, this is just kind of this grungy thing. It is. It's a process. We're not in Kansas anymore, Toto. You know, it's like not like we're just adding 2 things or subtracting. We're breaking them into parts, adding the x parts, adding the y parts, Pythagorean theorem, inverse tangent. This is the process. This process will be on the test. It'll just say, break them into parts, use sine and cosine, add the like parts, sum of the x, sum of the y. Pythagorean theorem, inverse tangent. I've bumped into engineers, electrical engineers, mechanical engineers, civil engineers, people who've had physics in college, and they're like, oh, vectors, I love those. And the reason they loved them is because it was systemic. This is the same way it works no matter what. It's like this the same-o, and people can just kind of go, oh yeah, just give me a couple vectors, I can do that. So we want to get to where we can do that. So here's the number 24 is kind of hefty because it's got 3. You could add any number of these, 3 forces. Let's draw the picture of this. 24. You've got a 20 Newton force at 180 degrees. First of all, for the 180 degrees, it's like, what the heck? What's going on is that it's really clean if you use the unit circle. And 0 degrees is in the positive x direction. That's 0 degrees. 90 degrees, you're going counterclockwise. Somebody last period said, oh, so we're going counterclockwise. Yeah, I don't know why. But 90 degrees is in the y direction. And that means that 180 degrees is over here in the negative x direction. It goes around to 270 is down here, and 360 you've gone all the way around the circle. There's 360 degrees in a circle. So here it says there's 20 newtons at 180 degrees. That's the negative x direction. That's just going this way. So there's 20 newtons going this way. But then there's 30 newtons at 90 degrees. Now, 30 newtons is going to be longer than 20, and it's going straight in the y direction. Now, this is tail to tail, but when we ultimately add these together, we're going to add them head to tail, so that they add up like this, to be a big giant triangle. And then there's 25 newtons at 135 degrees, and it says 45 degrees northwest. I hate northwest, southeast, any of those things. Just give me 0 to 360 and I'm happy. 135 is around this way, but it is at a 45 degree angle like this. We have 25 newtons. So these 3 forces are pushing it left, that way, and at an angle like that. When we add this head to tail, we're going to ultimately put it out here and just add it to the next guy. What we are looking for is a giant triangle that looks like this and has 2 sides. Because it's a triangle, well, 3 sides. But 2, an x and a y, and a hypotenuse. So here's how you do this. Just take your 20 newtons times the cosine of 180. If you go 20 newtons times the cosine of 180, and 20 newtons times the sine of 180, and then you're going to take 30 newtons times the cosine of 90, and 30 newtons times the sine of 90. And you're going to take 25 newtons times the cosine of 135 and 25 newtons times the sine of 135. You will be breaking them into parts. Cosine goes with the x parts, sine goes with the y. X, y, x, y. If you type that in your calculator that way, you're sitting really pretty. Because look what happens. In the x direction, when you take 20 cos 180, it's going to say negative 20. Because the cosine of 180, that's just in the negative x direction. It's going that way. And it's negative 1. And we take negative 1 times 20, you get negative 20. All of it is in the negative x direction. There is none in the y direction. When you go 20 sine 180, the sine part is the up and down part, the cosine part is the left and right part. When you take 30 cos 90, you're going to get 0, because cosine's left and right. It's all in the y direction. So when you go 30 sine 90, it's going to be 30. These are already broken into parts. You could always just go, well, the y part's 0 and the x part's negative 20. The y part's 30 and x part's 0. It's this one, it's going off at a weird angle, but it is a 45, 45, 90 right triangle. And so when you go 25 cos 135, the cosine and the sine of 45 is the square root of 2 over 2, 0.707, and 25 times 0.707 is 17.7 newtons. Now for the cosine part, that's the x part. When you type this in 25 cos 135, you're going to get negative 17.7 because it's going this way. And when you put in 25 sine 135, you're going to get positive 17.7 newtons because it's going up. So all you're doing in the first step is just taking the amount, the magnitude, times the sine or cosine for everybody. Now, that part, you're just breaking it into parts. X parts, Y parts, X parts, Y parts. The reason we're doing that is so we can add X's with X's and Y's with Y's. Probably the trickiest part of this whole thing happens right here. You're gonna add the X parts with X parts. It's secretarial, it's bookkeeping. If you start adding these two together, well, those are perpendicular. It's like, what are you doing? You can't add 17 and 17. You're adding X's with X's, so you have to add minus 20, 0, and minus 17.7, because it's going this way, and then it's going none that way, as it goes 30 up, and then it's going another so this side is negative 20 minus 17.7, it's negative 37.7 newtons. We're adding X parts with X parts, Y parts with Y parts. So this becomes negative 37.7 newtons. And then, look at your Y's. 0 plus 30 plus 17.7. So the Y parts, I'll do this in blue, that's gonna be none plus 17.7 plus an additional 30. Your Y parts end up being 47.7 newtons. Now we have a giant triangle. I need to do color because it gets crowded here. We have a giant triangle whose sides are 47.7 and 37.7. This was the whole goal of this, is break them into X parts, Y parts, add X's with X's, Y's with Y's, have one giant triangle, and then we do the Pythagorean theorem. The hypotenuse, the magnitude, the amount of force squirting this thing out this way is going to be equal to the square root of 47.7 squared plus 37.7 squared. You can put the minus sign in here, but when you square a negative thing, negative times negative is positive. And this thing's going to be, how big? I mean, 47 squared is about, I'm guessing, 50 squared is 2,500. And 37 is like 40. It's like 1,600. It's around, 41. I'm going to guess, call it 40, call it 39. 3,900 or something under the radical. It's going to be 60 and a smidge. I'm going to guess 60.2. I don't know what is it. 60.8 newtons. So what this is, that's how much you've got. The Pythagorean theorem is the amount. That's like if we all came up here and we came up to Gabe, and we had 3 people pushing on Gabe, and one's pushing this way, one's pushing that way, and the other's pushing this way. He's going to squirt out that direction, and he's going to feel more force going that way. Football players, you know this. If you're on the line, you're going head to head. Your forces are canceling each other out because you're smacking into each other. But if 2 or 3 people jump on one guy and push him that way, he has more force pushing him that way. And so these 3 forces are adding up to squirt out that direction. Now, the direction part, if you always take the ratio of opposite to adjacent, here's how I think of this. Basically, your sine part is the up and down part. It's the y. Sine always goes with y. The cosine is the left and right. So sine and cosine as functions, here's a little pre-calc stuff. The sine and the cosine always go between plus or minus 1. Because look what's happening here. So a sine curve looks, we had this on one of our board sheets, looks like that. That's the sine, that's a swinging swing, or whatever. And it goes between plus 1 and minus 1. Because the sine ratio is opposite to hypotenuse. It will never be bigger than 1 because you'll never have a leg of a triangle bigger than the hypotenuse. So it just toggles between plus and minus 1. The cosine curve looks almost like that. It's just out of phase by 90 degrees. And it goes between plus and minus 1. Because the cosine is the adjacent side to the hypotenuse, and the adjacent side's never going to be bigger than the hypotenuse. So cosine and sine, they toggle between plus and minus 1. But tangent is the weird one. Because tangent is the ratio of the opposite to the adjacent. So if you have a big opposite side, like let's say this is 1,000 meters long, and the adjacent side is 1 meter long. You can have this huge, it goes to infinity. When you get 90 degrees, then you've got all opposite and no adjacent. Divide by 0, it blows up. Or you could have something that has 1,000 meters for the adjacent side, it's like 1 meter that side. It can go from 0 to infinity or 0 to negative infinity. Tangent can be any number. The bigger it is, the more it's pointing in the 90-degree direction. So on this one, it's 47 to 37. So you always take opposite to adjacent, y to x. And so that's going to be second tan. And you just put in the ratio of 47.7 over 37. You can put the negative in there, and it'll give you a negative sign. That's going to be more than 45. This is my gut check. I know it's going to be bigger than 45 because a 37.7 to 37.7 is a 45. 45, this one's steeper, bigger than 45. I'm guessing 51. I don't know, 52, something like that. What's it come out to be? 51.8. I always guess 51 or 53. Sometimes it's 62. I guess 62. So it's a little steeper. Now, if you keep the negative sign in there, it says negative 51.8. And that's only because it's coming back around clockwise from 180. So your correct answer could be, I believe in this. A picture tells 1,000 words. If you draw a picture here and you call that angle theta, and you say it's 51.8 degrees, you and I are all on the same page here. It's like, bing, you win. I'm naming that angle theta, and it's 51.8, you're good. But some people are like, well, I want to use this one over here, and so when you take 180 minus 51.8, this comes out to be 126.2 degrees from the positive x-axis. I'm not going to play that game with you, but if you want to do that, you can give it either way. The answer key has both of those on there when you do it that way. Here's what tangent looks like. Since tangent is the opposite to adjacent, if it comes out positive, it could be a positive over here in what they call the first quadrant. It could be positive going up, but negative, positive y, negative x. It could be negative in this quadrant. When you go left and down, it's a negative over a negative, and that's going to be positive down in that quadrant. And if you go positive in the x, but negative over positive, it'll be negative. So your tangent just comes out negative or positive, depending upon which way the thing is squirting. I'm not going to get bent out of shape over pluses or minuses. Go take a math class, they can worry about that. I'm just looking for the angle. So if you come up with an angle and it happens to be negative because you took the y over the x here and you drop the negative, just say that's theta and it's like 60 degrees. And there you go, you're good to go. Now this is the bonus number 3 on the, oh, we did get the angle. So that's number 24. That's the toughest one on the bunch. Let me do a quick overview of those vector problems on the worksheet. I'm going to grade these lightly on this worksheet. They will return on force worksheets. We're going to be doing, I foreshadow. It's like we're going to add vectors. We'll do this. It's a process. Being a process, it's a few steps where you do this, then this, then this, this. It never changes. Break it in. Anybody? So, that is a bonus problem, number 3. That's if you're running on time and you got that. So, let's take a look at just the setup. You don't have to have a perfect picture. Number 1, 30 meters at a 45-degree angle north and east at 45. So it's 30 this way, and then it's 40 at 135, which is going to be going, it's actually a 90-degree angle. So it's a 30, 40, the answer's going to be 50. It's a 3, 4, 5 right triangle because it ends up being right. It's just a weird shape like that when you do it. Number 2 is 50 meters, 60 degrees northeast. And then you're going to have 70 meters at 150. It's doing a weird thing like that. 150 is 30 here. Oh, this one's also 90, isn't it? Because 30 and 60 is 90. So those are perpendicular. So it's a 50, 70, whatever that comes out to be, triangle. You can double check your answers. This is the kind of thing that I like. Number 23 is 20 meters per second east. Its velocity is speed, and 45 meters per second north. It's already broken into parts. It's all x and then all y. And so the answer is going to be, you just have to do the Pythagorean theorem and the inverse tangent to find the direction. Really good. That's kind of what we're doing on the problem. So what's on this crazy test tomorrow? There is a triangle. It's really a lot like worksheet 5. On worksheet 5, we've got some triangles here. And that's because if we project something at a funky angle, we're going to need to know how much in the x direction, how much in the y direction. We need to find those x's and y's. So here we are using sine and cosine. We're breaking this into parts to get the x and the y legs. There's one of those. There's some distance, rate, time problems. And when we say distance equals rate times time, we're saying delta x equals horizontal rate times time. That's the stuff we did on worksheet 1. In fact, if you look at our test 1, if you look at the first 4 questions on test 1, they are the 4 questions after the triangle on this test. It looks just like the front page. So you've got some distance, rate, time problems, and acceleration is change in velocity over time. That's 4 questions. It's a redo. So you can just do those. It's very similar to what we did. So make sure you can do those. Don't be botching your algebra on that. I think that was the biggest mistake people made, is they just took distance times rate. It's like, don't do that. Distance will be divided by rate to get time, etc. Then there's going to be 2 questions, and the 2 questions are like projecting an object horizontally off of a roof. And so when we do that, let me get rid of this triangle. It's like you got a roof, and it's on a tall building, maybe a 5-story building. And the question, let's say we launch something at 25 meters per second horizontally. Horizontally, distance equals rate times time. So the questions might be, how far does it travel horizontally? Watch out for those words. Horizontal and vertical. Vertical, y, horizontal, x. So how far does it travel horizontally? And say 2.5 seconds. So if we launch it, and it can fall for 2.5 seconds before it hits the ground, then distance equals rate times time. Horizontally, it's going to travel 25 meters per second for 2.5 seconds. It comes out to be 62.5 meters. Over half a football field. They tell you not to, it's illegal to throw things off of buildings and have them land on poor schmoes down below and everything like that. If you're at Kings Island and you drop something off the Eiffel Tower, you're going to get ejected from the park and probably in handcuffs because it's illegal to be dropping stuff on people who are unsuspecting. And so it's going to go that far away before it hits the ground, or before it even gets down here. We didn't say it's going to hit the ground. It could even go further if it falls for longer when you do that. Horizontally, distance equals rate times time. We love horizontal. Vertically, it's picking up speed. It's accelerating. Vertically, this equation right here becomes delta y equals the original y velocity times time. Now, if you're calling up positive, down negative, you could say minus 1/2 g t squared. What's the original y velocity if you throw it horizontally? What's the original vertical velocity if you throw something horizontally? How much is it going up and down right now? 0. It's got no vertical velocity because we're launching it horizontally. So this term goes to 0 because 0 times anything is 0. When you shoot things horizontally, the distance they fall is 1/2 gt squared. Half of 10 is 5 times 2.5 seconds squared. 5 meters per second times 2.5 seconds squared. That's 6 1/4 times 5. It will have fallen 31.25 meters. Now, couple things. Last period, somebody said, so do I use rate times time to get the distance, or 1/2 acceleration times time squared to get the distance? And I said, yes, you use distance equals rate times time for this horizontal, and you use 1/2 gt squared for the vertical. You just have to keep the two separate. It's a bookkeeping thing. It's about being careful and thinking, oh, this one's up and down, and this one's side to side. Horizontal, vertical. Yeah, and so it has gone over some 62.5 meters, but fallen 31.25 meters at that point in time. Now, that's because it's picking up speed and it hasn't picked up too much yet. Think about this. Okay, first of all, don't borrow money from the mafia. But if you borrow money from the mafia and Guido comes to get you and throws you off the 13th story of a building, it's not the horizontal rate that Guido throws you off at. You know, he threw you off at 3 meters per second. Woo-de-doo. It's that high speed you reach because you're falling through such a great distance, and it's really the sudden stop that gets you. It's not the fall. It's that sudden stop. But if you're riding your bicycle and you're riding down the street and you hit a little ditch or a bump and you go flying over the handlebars, it's not so much, we used to buy for my nieces and nephews, they're now older, but for all my nieces and nephews, we bought them helmets for bicycles all the time. When they started riding bikes, that was our gift, helmet. Because if you fall from this height on your bicycle and hit your head on the concrete, it can be damaging. They say you should wear a helmet. But if you're riding down along, and let's say you have a helmet on, and you're in a bike race or something, you're doing, say, a biathlon or something, you're riding your bike, going around, triathlon, whatever. If you're riding really fast, it's that high speed that's gonna hurt when you hit the concrete. If you hit some gravel or something, you're gonna slide out. Sure, it hurts to fall this far, but it's that high velocity horizontally that's gonna get you. The longer this goes, the faster it's gonna be moving downward, and this distance is gonna outreach that distance in the end of this thing. 25 meters per second, shooting it at a pretty good rate. I mean, you're kicking a soccer ball or a croquet ball pretty darn hard to get it to go 40 miles per hour off the roof. But it will eventually go 40 miles per hour down if you have long enough for it to fall. Now, that's the first couple types of things, but then it goes, okay, well, how fast is it moving when it falls for 2.5 seconds? And so there's the velocity part of this. So the velocity, when it gets down here, it's going to be moving this way, and it's going to be moving that way. So horizontally, there's no air resistance. It's going to be moving at the same speed. So if you hit it 25 here, it's going 25, 25, 25, 25. It's going to be going at 25 meters per second across. If it falls for 2.5 seconds, and it's picking up speed due to gravity, I like to think of this one as final speed equals original speed plus acceleration times time. What's its original y velocity? You just said it. None. And so when you fall, you're picking up 10 meters per second every second for which you fall. And if you fall for 2.5 seconds, you're going to be going 10 times 2.5. You'll be traveling down at 25 meters per second. This one's kind of nice, and that you'd be traveling that way as you're flying down there. And so it'd be 25 squared plus 25 squared, the square root. 625 and 625 is 1250. that's gonna be like, I don't know, 35 meters per second or something like that. Heading down at a weird angle. And then for the angle, so we are, if it says what angle, we are doing the inverse tangent. That's second tan, and you take opposite over adjacent. 25, the y part over the x part, but the inverse tangent of one is 45 degrees. It's a 45, 45, 90 right triangle. It does this. So that's a sequence of 9 or 10. You get to pick one, and the other one's very similar to it. The other one becomes bonus points, because we're very conscientious about the 45-minute time slot that you're taking this thing in. So you pick one. If you do them both, you get bonus points. And then the last kind of problem we have on here is projectile, where you've got a thing being shot or launched at an angle, like the soccer ball, the golf ball, chucking it, hitting a golf ball. Maybe you're chipping it. When you chip, you use a wedge. You're kind of out from the green. You miss the green a little bit, but pop it so it's got to bounce over the lip of the edge. You want it to fly and land. And ideally with a chip, you get a little bit of backspin or something on it, so it stops dead. It doesn't keep rolling. And so you're chipping towards the green. Here's your hole, and you're over here. You want to be chipping it close to the thing. So you're going to be hitting the golf ball at an angle and a speed. Let's say you chip it at 15 meters per second. That's a pretty good chip. It's going to go way over there. Maybe you're chipping from 50 yards out. I don't know if that's called a chip at that point in time. And so then, let's say we shoot it at a 60-degree angle. What's it going to be? What's the horizontal velocity? What's the vertical velocity? How do you find the horizontal velocity? What's horizontal velocity? What's the other name for horizontal velocity? Horizontal velocity. Elliot. Horizontal velocity. X. Yeah, piece of X. That side right there. Vertical velocity, Y. And so that's going to be the cosine part. 15 cos 60. Now cosine of 60 is 0.5, which is sine of 30. And so this is going to be 7.5 meters per second as it goes flying that way. And for the Y part, it's the sine. So see, you are breaking down a vector into its parts by doing the hypotenuse times the cos, hypotenuse times the sine. You just got to make sure you get x with x and y with y. 15 sine 60, that's not as pretty. 8.66 is 4.33. Oh, it's real close to 8, 4, 12, 13 ish. 8.66, 4.33. It's really close to 13, isn't it?
12.9.
It's what?
12.9.
12.9. Okay. 12.9 meters per second. Now, we can start to do some other things. Look. How long does it stay in the air? How long does it stay in the air? It's going up at 12.9, and it's slowing down 10 meters per second every second. For how long does it rise? How long does it take you to go from 12.9 to what's the vertical speed at the top? Vertical speed at the top. Heard it? 0. So how long does it take you to go from 12.9 to 0, slowing down at 10.9 meters per second? The time up is equal to your original y over gravity. 12.9 divided by 10, you're going to go up for 1.29 seconds, call it 1.3 seconds. And then by symmetry, you're going to come back down for 1.3 seconds. Total time of flight, twice 1.29. It's going to stay in the air, t total. These are all up on the top of the test, but you don't want to go hunt them down. If you do the worksheet, take a look at it, total time's just twice the time up, so that's going to be in 2.6-ish, 2.58 or something like that. Now, you can figure out how far does it go horizontally. Horizontally, I've erased it, distance equals rate times time. 7.5 times 2.6 seconds. I don't know, that's 15, and 4.2, that's like 19.2 meters. Sounds good. 7.5 times 2.6. Oh, I thought you were typing. What? 19.5 meters. Isn't that the hard part of golfing? You're out there about 40 yards, and you have to guesstimate how far am I from the pin, or how far away am I? And so which stick do I use to hit it? And then I hit it the same way every time. This is why they have driving ranges. You just go there and you just whack balls to see how far does it go when I whack it with this stick. And so you have to guesstimate how far away the stick is. And once you know how far away it is, that tells you the stick in the hole. You figure out how far away the hole is, you pick the right club, and then you just hit it the same way every time. Because if you're trying to hit it weird ways, I mean, maybe, anybody golf? Anybody have any like more finesse than that? I mean, I just hit the ball and try and hit it the exact same way so it goes the distance I know it will go, and I guesstimate that so that it ends up close to the hole. And so it will end up 19.5 meters away because I use the right stick to hit it and make it go 19.5 meters when I do that. And then I just have to aim in the right direction. My problem is when I hit the golf ball, I don't know which way to slice or hook, but it goes way off to the right. I think that's a slice. But so I have to just aim my body sideways. I just work it. I've never golfed enough to actually be good at it, but I just figure since it's gonna, maybe that's a hook, hooks off to the right, I'm just gonna aim my body this way, aim at the ball that way, and it's gonna come right back onto the fairway that direction. So I just, and it's gonna go. It's kind of like bowling. If you know your bowl and it goes off to the right, you aim a little to the left as you do that. Work your shot. And so now the other question would be, I don't know, another question we can't. That's how far it goes, how long it's up in the air. You could be. This one's a nice one. How fast does it hit the ground at? Well, when it hits the ground, if it's on the same level, it's going to be going 7.5 meters per second across, and it's going to go up and stop. It's going to then get to that height, and it's going to come back down. It's going to be moving just as fast here as it was over here, so it's going to be going down at 12.9 meters per second, and you're going to have it, it's going to hit the ground at 15 meters per second, and an angle of 60 degrees below the horizontal. There's some symmetry going on here, and so we'll be doing that. Questions that you have over this stuff, because when we come back tomorrow, this is what we're going to do. And so bring a calculator, don't be running late because you want to use the maximum timage. We're anxious about time. There are basically one of the two, 9 or 10, that's a bonus question because you pick one of the two and then the other one is optional if time allows. And then you've got actually a bonus 1, 2, and 3 at the end. You got tons of bonus on this. If you get stuff done, you'll have time so that you get all the points. But there's even some bonus options here. Yeah. Do what? Well, there's a bonus question that it has a thing being projected off of a hill, so it's being launched, and so it's doing this. That's a bonusy question. There's the vector addition. And then the other one is the third one that's up there. Oh, it's a follow-up question on this thing. It's asking where its location is somewhere along the pathway right here. Finding the delta y and delta x is a little bit more intermediate. So there's a follow-up question on the previous one. It says for bonus, where is it at this time? And we'll find the horizontal and vertical position, and that's if you're looking for x. Yes. What? How long does it take to travel this far? This is great.